here I Professor Lin is professor at the Qiang University, and he was the director of the Institute of Bioengineering. He's going to be entitled Digital Twins to Improve Process Efficiency and Sustainability for Continuous Biomanufacturing. The floor is yours.
Okay. Thank you, Chairman. Good morning, everyone. I mainly work on process development of bioseparation. So just a few years ago, I moved to digitalization, modeling, and process control. So I'm newcomer in the field of the process system engineering. So I'm so glad to have this opportunity to have a presentation here. Today I would like to share with you on our preliminary research on digital twin for continued biomanufacturing. As we know, now biopharmaceutical grows very fast, but also meet strong competition and challenge. So the company also needs to think how to improve the process efficiency and reduce the cost. For that, continuous manufacturing is a hot topic, and FDA, ICH also publish some guidance to push to encourage the companies to try continuous biomanufacturing. And many companies also did a lot of tests and demonstrate the continued bioprocess can have higher process efficiency and higher productivity, and can also reduce the cost. And the continued process also showed less environmental impact with smaller footprint, less energy, resource, water requirement, and also field waste. But the continued process is quite complete with a lot of dynamic control, so it's quite difficult to design to control a continued process. So what we can do is, I think maybe we can find some support from the smarter manufacturing, especially on the digitalization and smart control. So if we can build up a digital twin system, we can connect the physical world and cyber world. We can, the digital twin can improve our understanding of the process. Then we can design a better process. Maybe we can make a better process control. So I just showed here a typical continuous process for map production. Now, continuous cell culture is quite good. So the difficulties are on the downstream, especially on the chromatography step for continuous capturing and continuous polishing. So for the continuous capture with protein A affinity chromatography, normally we use one column batch chromatography. We need to run the loading under low flow rate, so the productivity should be low. We also need to stop the loading at the load breakthrough percentage. So the capacity utilization is also low, only about 50 to 90%. So for the continuous capture, we can connect to column for the capture. So the protein breakthrough from the first column can be captured by the second column. So for the first column, we can stop the loading at the higher breakthrough percentage. So we can increase the capacity utilization. Then we can turn the column in turn, we will have the continuous capture. So the concept is quite easy to understand, but the real application is quite complete. We can use 2-column system. We can also use 3-column, 4-column system. We need to take about the first column protein breakthrough at a higher breakthrough percentage. We don't want the protein breakthrough from the second column. We also need to balance the time for different columns. So, which one is the best? How can we find the best operation condition to improve the productivity, to improve the capacity utilization, to reduce the buffer consumption? Normally, we need to do a lot of experiments for the process optimization, maybe take several months to find a suitable conditions. In order to improve the process development, we build up the chromatography models. So we just use few breakthrough curve, we can obtain the model parameter. Then we can calculate the breakthrough curve under the different conditions. So we can use the model to study the influence of the different operation conditions, and the model can tell us which one is the best. So we just need to do some few experiments for the validation. For the scale-up, we can also use the model to help us. Now, the model-based optimization method has been used by some Chinese biopharmaceutical company to help them for better process development for a real industrial case. In order to help the people from the industry to use the model, so we also developed a software for this page, for the parameter feeding. Then we can use the model to calculate the different operation model. Then the model can help the people for the process development. So the people from the industry, they don't need to know the model. They just need to input some necessary index. Then you can use the software to find the best operation conditions. And for the polishing step, normally we need to separate some impurity, but sometimes it's quite difficult to separate because the impurity have quite similar properties to the main product. So we also need to do a lot of experiments for the process development. For that, we can also find help from the model. Just as I showed here, for the ion exchange chromatography, we can use the SMA model. After the parameter estimation, we can use the model to help us to calculate the erosion curve for different components under the different conditions. So we can use the model to help us for the process optimization. I just showed here the computer screened about 800 conditions. It takes only about 20 minutes. But we want to do the experiment, 800 experiment, maybe we need to take 1 to 2 years to finish it. So for this spatial charge valence periodization, we use the model-based optimization method. We can improve the yield from 50% to 87%. So we also developed a software to help people to use such kind of model. So they can just input some necessary data, they can use the model to help them for process development. And for the continued polishing, it's quite complete. It's quite difficult to find the best operation condition. So it's impossible to find the best condition just with the experiments. But when we have the model for one column, we can expand it to the mixed column system. We can calculate the peak under the different operation model, under the different operation condition. So the model will help us to find the best operation condition. For the whole place, we can also use some process simulator. Here we use the SuperPro Designer. We can build a whole process in the computer. So such a kind of model can help us to do the whole process of optimization. So here we build up a continued process for method production. We also combine the chromatography mechanism model to the process model. So we can use such kind of process to start the influence of factor from the continued capture to find how it influences the whole process. So we can use the process simulation to find the best operation condition for the whole process. We can find the condition, just as shown here, to improve the equipment utilization to reduce operation cost. So, okay, I have shown you how we can use the model for process describing, and we can also make some prediction for the process development. So we call it the first level digital twin, select digital twin. When we want to use the model for the process control, so we need to face the real-time response. So we need to improve the select level to the second level, dynamic level, to face the real-time response. So let's go back to the continuous capture. For the continuous capture, we need to face some dynamic control. The first is on the change of the loading concentration. So if we have the model, we can use the model to calculate the protein breakthrough under the different conditions. So we use the model to help us to obtain the right control at the fixed breakthrough percentage. So during using, the reason capacity will decrease. We can also use the model to describe the trend of the reason capacity change. So we can also use the model to help us find the right control. But we also find some limitation for the holding, for the model calculation, because we need to solve for the partial differential equations. We need to wait several minutes to obtain the curve, maybe sometime 10 minutes. So for the process development, it's no problem. We can just stop the work, take a cup of coffee and go back, we have the result. But for the process control, we need to real-time respond. We want to increase the calculation speed. So for that, we introduce the Qiang. We can use the model to help us to solve the partial differential equations. So we can obtain the curve just in several seconds. So in the future, we want to build up a dynamic digital twin system. So we can use the model to calculate the protein breakthrough at the different column. We can make a right control to improve the productivity, to improve the capacity utilization, and keep the higher yield. And for the protein polishing, we also need to face some dynamic change. Maybe need to think about the loading change, peak fluctuation. When we have the model, we can make a prediction. So we try to build up a dynamic control system. At the inlet, we measure the loading concentration and concentration. Then we can use the model to predict the peak after the chromatography. Then we can make a decision how we can calculate the peak to obtain the high purity product with a high yield. So we also cooperate with one Chinese company called Hens to build such kind of digital system in their lab. We connect the simulation machine, HPLC analytical machine, and the model. And the model system have a quite good result. They can make a right control. We also published one paper to show how can we build up such kind of digital twin system. We can find here the results. The model can fit the experiment in quite good way, so it can make a very good control. I also built up a similar system in our lab. Now we put the model in the cloud. The new system is ready for the industrial use because it's under the ISA 88 controlled standard. So in the future, we also want to build up a digital twin system for continuous polishing. We can use the model, we can use the AI to help us to predict the peak under the different conditions. Then we can make a right control for the continuous polishing. So now we have the first level static dynamic digital twin and the second level dynamic digital twin. In the future, we hope the digital twin will have a self-learning and adaptive ability. So the digital twin system will become more and more smart, doing wrong and wrong. So it can help us to solve everything. So maybe in the future, for the next generation facility, we have a real-world system. We also want to have a digital twin system. Then the digital twin system will analyze the big data from the real world, then make a right decision back to the real world system for smart control. So I would like to take a few minutes for a brief summary. So now we are working on the integrated continuous process to improve the process efficiency. Maybe in the future, I need to do more research on the process system engineering to improve the process. We want to move it to the smart control. We want to move it to the smart manufacturing. And for that, I think we need the support from the digital twin. So in the future, we hope we can have a highly interactive continuous process. We also need a lot of PAT to obtain a lot of data from the real process. Then we can transfer the data into the digital twin platform for the modeling, for the AI analysis, for the risk evaluation and process optimization. Then we can make a right decision, then back to the real world system. So in the future, we have a real world system, real world physical system. We also have a digital cyber system. We can use the digital twin to connect them. So in order to build up the digital twin system, we need to develop some new tools. The one way is on the model base. The another way is on the data stream, maybe AI ways. So we need to sometimes we need to combine them. So last year we also established our own website. We put the tools developed in our group into our own website. So if you are interested, just tell me, I can open it for you. So that's all for my talk. I hope maybe in the future we can find some chance for the cooperation. Because I think I need a lot of help from all of you. I need to do a lot of research on the process system engineering. Okay, thank you.